So we've talked about homogeneous equations. Now let's talk about inhomogeneous. So let's just take an example. So what does it mean? The difference between a homogeneous equation and an inhomogeneous equation can be thought of as, at least in the context of masses on a spring, the inhomogeneous term can be thought of as an external force acting on the mass. So in the past, we had a mass on a spring with resistance. So there were two forces acting on the mass. There was the spring force and the resistance force. Now we're going to assume there's a third force acting on the object, some kind of external force. In this example, the external force is this, 12 times an exponential decay term. So we're going to write a differential equation and solve this problem with an external force. So again, homogeneous equation means the right-hand side is 0. You have, that is, when you collect all your stuff with x's, x primes, x double primes, all the x and all of its derivatives on the left side, you have 0 on the right. For an inhomogeneous equation, we have some kind of function of the independent variable, in this case time, on the right-hand side. So how do we solve an equation like this? Well, to find a solution, there are lots of solutions to this equation. The first step is to find one of them, and you can usually find one of the solutions by guessing. Simply guess that the solution x of t will be similar to the right-hand side, and this usually works, pretty surprisingly. So we simply guess that x of t will be some constant times e to the minus 0.04 t. And it turns out, if we choose the constant correctly, we can make it work. So we plug our guess into the differential equation, and we get this. So this is obtained by taking x prime prime, plugging it in here, taking x and plugging it in here, and you end up with all this. Now divide by e to the 0.04 to the negative 0.04 t, and you end up with concluding that a is 19.93. So we found a solution. X of t is 19.93 e to the minus 0.04 t. This is no doubt a solution to the differential equation, but like I said, it's not the only one. In fact, it's not a solution to the initial value problem. It solves the differential equation, but it does not satisfy the initial conditions. We wanted x of 0 to be 0 and x prime of 0 to be 0. So how do we deal with the initial conditions is the question. So we got to here. We found a particular solution, but it wasn't a solution to the initial value problem. So we denote this solution by x sub p for particular. And then how do we find other solutions? Well, to find other solutions, you have to solve the complementary homogeneous equation, obtained by replacing the right-hand side with 0. So we do just that. Take the same equation, replacing the right-hand side with 0, and now we have, by solving the characteristic equation, you get r equals 0.65i, and then using Euler's identity to interpret e to the rt as a cosine plus a sine, you end up with this solution to the complementary homogeneous equation with two arbitrary constants c1 and c2. And this is denoted with a subscript c for complementary. And then the general solution to the inhomogeneous equation is xp plus xc. This is always the case. So x is the particular solution plus the complementary solution. Now we solve the initial conditions. So I define x of t to be exactly what I wrote here. And then I solve the initial conditions for c1 and c2. And I find that these two numbers for C1 and C2. So we conclude that this is my solution. So this was the particular solution, and then by adding these, it's still a solution to the differential equation, but with the kicker that it also satisfies the initial values of x of 0 equals 0 and x prime of 0 equals 0. So that is how you solve an inhomogeneous equation. You find a particular solution, solve the homogeneous complementary equation, and combine them together and find the constants. So we have this solution. I thought I'd plot it for you. Recall that the external forcing function was 12 e to the minus 0.04t. So it's an exponentially decaying forcing function, which caused our mass to oscillate back and forth, but it was shifted. And then as the exponential forcing function decayed to 0, the mass got back to oscillating about the equilibrium point, x equals 0. So you can, if you were to plot the axis of oscillation, it would be it would be this function here, 19.93 e to the minus 0.04t. So that's precisely the axis, and then we just have oscillation about the axis. So we have a differential equation now with a sinusoidal external forcing function. This problem's a bit more interesting. We have a resistance of 10 and a spring constant of 9 and a mass of 1. We're going to consider these initial conditions. X of 0 is 1, x prime of 0 is 0. And we're going to solve this by first finding a particular solution by guessing. So we do that, and we guess that the particular solution will have a similar form to the right-hand side, which in this case means using a sine 2t plus b cosine 2t. When you plug that into this differential equation, you get a whole bunch of stuff. When you combine like terms, you get this. And so we need this coefficient of sine 2t to be 1, and we need the coefficient of cosine 2t to be 0. It's kind of like doing partial fractions. You just need the coefficients on both sides to match. And that leads you to equations in A and B, which you can solve. And you conclude that if this x sub p is going to be a solution to the inhomogeneous equation, we need A to be negative 1/85th and B to be 4/85ths. And so we plug those informations into our particular solution, and we find this is our particular solution. On the other hand, the associated complementary homogeneous equation has this characteristic equation with roots -1 and -9, which leads us to the complementary solution C1 e to the -1t plus C2 e to the -9t. And then our general solution is obtained by taking our particular solution and adding our complementary solution. And so we get this, and at this point we can use our initial data to figure out what C1 and C2 are. So we're going to do that, and so we use the same code as before, the same idea. You let x of t be this expression, and you figure out what C1 and C2 are, such that the initial conditions are satisfied. And you get these values for C1 and C2. Notice I chose to use the solve function because I thought it would be nice to have the exact fractions instead of decimals. So if I had used nsolve, it would have given me decimal answers instead of these fractions. So this is our solution. X of t is all this, and that's the solution to this initial value problem. It solves the differential equation and satisfies the initial values. Alright, now let's plot this as well. It's an interesting looking function. Basically, these terms are dominant at first, but they rapidly decay to 0, and what you're left with is a sinusoidal function for larger values of t. In fact, you can recall that this part was our particular solution, and this part was our complementary solution. And if you plot the two of them separately, then you see how they add together to give you the actual solution to the problem. Another word for this solution is it's also called the transient solution, and this is called the steady periodic solution. This one's steady, it's periodic and does the same thing forever, and this solution is transient, meaning that it goes away after a short time. In the long term, the solution is a sine wave. So, by the way, I wrote some notes about how you can interpret a sine omega t plus b cosine omega t. This is supposed to be covered in pre-calculus, actually, but often isn't covered as well as it should be. Anyway, you can use these trigonometric identities. A sine theta plus b cosine theta can be rewritten as c cosine theta minus phi, where c is this and sine phi satisfies these guys. So in the previous problem we had a complementary solution of this, and then you can rewrite this, this is a sine, call this theta, plus b cosine, call this theta again, and you can rewrite it using this identity as 0.0485 cosine 2t plus 0.245, where phi, the displacement angle, the phase displacement, is found by taking the arctangent of b over c over, or I'm sorry, a over c over b over c. Anyway, this computation is done using the generalized arctangent function. I suggest you read the documentation in Mathematica for what exactly the arctangent function does when you put two arguments in. It's very useful for rewriting these sorts of things as a single cosine function. So this is how you find c and phi using this trigonometric identity, and thus you can rewrite these more complicated expressions and figure out what the actual amplitude and phase displacement and frequency are. Well, the frequency doesn't change. Let's talk about resonance now. So before we talk about resonance, however, we need to first talk about an example of what resonance is not. Here's an example of a problem where we do not have resonance. Suppose you have a mass of 1 kilogram on a spring with a spring constant of 9. Let's also suppose the resistance is 0, and let's suppose we subject our mass to an external forcing function of 5 sine 2t. Let's set up and solve the differential equation with the initial values that the object starts at rest. That's equilibrium position. So, here's our equation, as usual. The characteristic equation gives us a complementary solution of c1 sine 3t plus c2 cosine 3t. And then for the particular solution, we guess that the particular solution will have the same form as the right-hand side, which is a sine 2t plus b cosine 2t. Substitute that into the differential equation, combine like terms, you get this. Now set the coefficients equal to the coefficients on the right-hand side. So we need 9 minus 4a to equal 5, and we need 9 minus 4b to equal 0, which immediately gives us a equals 1 and b equals 1.75. No issues there. And so the general solution is the particular solution plus the complementary solution, which, so here's the particular solution that we found, and then here's the complementary solution that we also found, and then we use the initial conditions to find that C1 is this and C2 is that, using the same Mathematica code that we've been using so far. So you end up with this solution to the problem. Alright, so we have a solution. Here's a plot. It's pretty chaotic, but it's also periodic. It is repeating itself, as you can see. You can see it doing the same thing over and over again with period. It looks like just over 6 to just over 12. So the period is approximately a little bit more than 6 seconds. Anyway, that's what the solution looks like. Make of it what you will. The object goes up to a height of 4, down to a height of a little more than 3, it looks like. It's doing what it's doing. But now something interesting happens if we choose a different forcing function. So if we take the mass to be 1 and the spring constant to be 9 as before, and this time, and no resistance, but this time subject the object to an external force of 5 sine 3t. The only thing I changed is the frequency of the external force. I changed it from having an angular speed of 2 to an angular speed of 3. So let's look at this differential equation. Again, we find the same complementary solution, C1 sine 3t plus C2 cosine 3t, just from the characteristic equation r squared plus 9 equals 0. And then for the particular solution, we guess that it'll have the same form as the right-hand side, so we guess a sine 3t plus b cosine 3t. But when we plug it into the differential equation, we get 0 on the left-hand side and 5 sine 3t on the right-hand side. And this is clearly not true for all t, so we conclude that this is an incorrect guess. So what happened? Why did our usual guess not work? No matter what values of a and b we choose, we just get 0, no matter what. I encourage you to check that fact. This occurred because a sine 3t plus b cosine 3t, that was our guess, it matches the complementary solution. And when your particular solution matches the complementary solution, well, you're doomed to get 0 on the left-hand side, because that's exactly what the complementary solution was supposed to do, was give you 0 on the left-hand side. So when this occurs, when the particular solution's form matches the complementary solution, you have to replace the particular solution with the same thing, but multiply by t, your independent variable. When you do that, and you plug this into your differential equation, it's a lot harder now because you have to use the product rule and stuff to figure out what x prime prime is. It takes a lot of work, but computers can be helpful. So this is our second derivative. You plug it into the differential equation, and you get this. And then we conclude that a is 0 and b is negative 5/6. So we conclude that our particular solution is negative 5/6 t cosine 3t. So we got negative 5/6 for b and 0 for a. So negative 5/6 t cosine 3t is our solution to the inhomogeneous. And so with this particular solution and this complementary solution, we add them together to get our general solution to the problem. Then we solve the initial values, getting 5/18 for C1 and 0 for C2, using this Mathematica code. And so this is our solution to the initial value problem. And if you plot it, you get this. So the 5/18 sine 3t is not very interesting. It's not really doing much of anything. You can barely even see it in this picture. What's really dominating this picture is the t cosine 3t. The t is causing the amplitude to increase linearly forever. This object is just oscillating back and forth with ever-increasing amplitude for all of time. So let's look at the last two problems we did. The last one, the 2 problems ago, we did this one with sine 2t for our forcing function, and we ended up with this solution. When we took sine 3t, we got this solution. Looked pretty different, and the results were very different graphically too. This is what the graph looked like for when we had a sine 2t for our forcing function. But when our forcing function was sine 3t, all of a sudden we ended up with this ever-increasing amplitude. Now, this is a dramatic effect. I mean, if you look at this solution, the highest it ever goes is 4. Just short of 4, it seems. But if you look at this solution, the amplitude, look, it goes past 4 very early on and just keeps growing and growing. Reaches any amplitude imaginable. So, what in the world caused our mass on a spring to behave so differently when this was our forcing function versus this one? Well, this phenomenon is called resonance. It occurs when the forcing frequency, that's over here, matches the natural oscillating frequency of the system. The way you can think about this is that when you have a mass on a spring, it has a natural rate that it would oscillate if you were not acting on it with any external forces. If you were to just pull the mass down and release it, it'll just go up and down at a certain frequency. Now, if you introduce an outside force acting on the object, if the frequency of your outside force doesn't match the natural frequency, it will sometimes cancel and sometimes work synergistically, and you end up with this chaotic behavior where sometimes they're working together and sometimes they're working against each other. Whereas if your outside force matches the natural oscillating frequency of your system, then it always works synergistically. The outside force is always pushing down when the object wants to go down, and the outside force is pushing up whenever the object wants to go up. And that just causes it to oscillate ever more wildly for all of time.